very general question on the data. What part of this data is likely to come from a distribution with finite size? And that is almost an unsupervised classification, but it did involve this input of this knowledge that galaxies can have finite size and stars cannot. In this situation, so what you're kind of heading towards are totally unsupervised methods. So you could take this plot and just say to the computer, tell me what kinds of things are in this plot. And there's a huge literature on such methods. But in my experience, none of those methods do as well as something that is at least seeded with sub-minimal information. So here I seeded it with the information that I think that the galaxy models are in a blob around here and the star models are in a blob around here, and it did the work. If I didn't seed it with any information at all, it would be very hard to find a method that found that this was two crossed populations.
Yeah, very naively, I would draw these ridges by hand.
I know. That is true, and you can certainly write a method that does that, but then you'll find that you've written a method that's a ridge drawing method. I mean, I'm speaking a bit glibly, because there are certainly people who work in unsupervised classification who would look at this and say, yeah, we can nail that.
But then you wouldn't know which were stars and galaxies.
No, but you could take one spectrum and then you'd know.
So that's a model.
Well, yeah, you could then tag later. I mean, certainly people who are using methods like PCA, many people in this room use methods like PCA, they're running just a generic linear algebra method on their data and then interpreting the results as having a physical meaning. So that's a similar thing you could do here. You could ask for clustering in here and then ask, are the clusters, are these star-forming galaxies and these are dead galaxies and these are starburst galaxies and these are hot stars, whatever. Maybe it would come out like that. But it requires that follow-up, which I agree with you is kind of a model.
I have a question to the same point. If you just start, you showed us that the models converge by comparing the numbers of data points which lie near the model. Could you start with something where you have the stars going from here to here, very broad, flat distribution, and another flat distribution from here to here? Would this converge in the same way? Because then you would imagine all these model buildings.
Right, yeah, good. So imagine you just put galaxy models in a huge grid that covered this whole space and star galaxies in the same region. No.
What I proposed was just to say, okay, stars here, all area,
yes, right.
galaxies here, all area.
So at some point it continuously degrades in its quality as you open up the space of the models. So it is true that it also related to your point, it is true that the more information you put into the system ab initio that's correct, the more correct information you put in, the better. So this method is designed to be very robust to incorrect information, as I showed, but in fact, the more correct information you start with, the better off you are in the end, for sure.
Very fast.
And much faster.
Okay.
I don't actually have a question. I just want to say that anyone who wants to catch the 4:30 bus might want to jet like the couple of people who have already done. Bye.
Dustin Lang taught me much of what I know.
Yeah, so back to the unsupervised method point. If you could run a completely unsupervised method on this, wouldn't it do better at maximizing the likelihood for that suite of models that don't exist for where the galaxies are not well explained by any model? Right, so you made a point at the start that there were models models exist that data exists that aren't fit by any model.
Yes, right.
Would the unsupervised methods recover those?
This is actually something I think about a lot, and VV and I work on related subjects. One interesting thing is, if you're in a location here where there is no model, it kind of makes sense to ask the system, well, do you want to promote one of these objects to being a model?
Right.
And it will, and it's very nice. We could just take everything that's beyond the last model here, throw it all in as models, and then one of them would light up as the model, and that would be the archetype for its class, and you can build new archetypes this way. So one of the things that Vivi and I work on, and lots of people here work on in one form or another, is how to promote observed objects up to archetypes, or even collections of observed objects up to archetypes.
Such
So
as
this is a very
binary
generic
stars,
method
if
for
you
doing
model only single stars.
Say again?
If you model only single stars, binary stars.
Exactly. Right, exactly. That's another good example. In fact, that's getting us in trouble right now with our work that we're doing right now in Cosmos, is that we have only single star models, and the binary stars all show as outliers, but we can see they're clearly stars, so we just throw them in and then they become models.
If you were to change the question, and we don't want to discern stars from galaxies anymore, but we want to know which models are good and which are bad, would that be possible the same way? Does the size with which a symbol comes out here really tell about the quality of the model? This is bad and this is good?
To my knowledge, actually, this is the only way to assess whether a model is bad or good, is by comparing it at the marginalized likelihood level. So if you have two competing models for what galaxies look like, I think the only way to compete them is by writing down the marginalized likelihood for the data. I don't see any other consistent way to compare the two models. So it is exactly that. Now, you might have been asking whether your model is absolutely good rather than whether it's relatively good. And as for absolutely good, that's a much harder question, whether the model is absolutely good. But in terms of relatively good, I think this is the only way to compare two. Now I'm talking about supermodels, like you come in with your Bruegel and Charlotte models, I come in with Starburst 99 and we go head to head. I think the way we go head to head is here. I think that is the way to do it. I thought you were going to ask the other question, which is, does this, if you run this, do you then make better predictions about star formation histories and redshifts and other things that go into the galaxy models? And the answer to that is hella yes. One of the things we're doing with this, if you then, this is all projected down to this marginalized thing, now unproject it and look in the model space, we find we do a very good job of doing photometric redshifts this way. So because we upweight the models that are doing a good job of explaining the data, those make good redshift predictions.
So there are very small spots next to very big spots. So it's
There are, but those very small spots just don't turn out to be, they do not add information, it turns out, in like the redshift direction. If they did, and it would have to be information about the redshift direction that is not contained in the pan-stars color. So it's kind of, what this really is kind of an information locator. It's saying that these models contain enough information to describe the data set. And if you want more information than that, you better take more data. It's kind of the attitude.
So you can differentiate stars from galaxies both by shape and by ACD. How, when you've shown us how this works and that it should be done, it hasn't been done for big survey. How computationally expensive is it to reprocess the entire Sloan survey to play this exercise, not just on a handful of mock data?
It is not computationally expensive. It was expensive on my laptop to run on this, but when you think in terms of, so I have several comments. One is, it's only as computationally expensive as your model space is large, is the first thing. And then the second thing is, you can update these models in a very online way. You don't need to, you don't actually need to grind on all of the data simultaneously. Every new data point you see improves your models. And so you can actually just run through the Sloan data asking for each chunk of Sloan data, what does it say about your models? And you can improve the models online. So in principle, this can be done as a survey progresses. So as pan-stars progresses and information in colors improves, information about the point spread function improves, and information about time variability improves, the likelihoods of all the models should improve. It should be possible to run everything online as you go. So no, it's not hard.
Okay. I would like to say a final word. There you see there's a lot of audience, and I would take this as an indication that this talk is an archetypical house cooking talk. Thank you very much.